Click the bell icon to get latest videos from Ekeeda.
Hello friends. So today in this chapter we are going to derive Einstein's coefficients. Now why do we require first of all Einstein's coefficients? Einstein's coefficients tell us the probability of the stimulated emission to that of the spontaneous emission. So, in order to derive this, first of all, we need to consider the interaction of radiation with matter. And by radiation, I mean photonic radiation or the light radiation. Consider matter that is comprised of only two energy levels. This is a very hypothetical case that we are considering. And E1 is the ground state and E2 is the excited state. The total number of atoms in the ground state, let us assume that to be N1 at a particular temperature, and the total number of atoms in the excited state, we consider them as to be N2. When radiation falls on this stack of atoms, radiation meaning a radiation of density rho. So when this radiation density of rho falls on these atoms, we are considering only one atom over here, what happens is an electron from the atom will absorb this particular energy and will get excited to the higher energy state. So this is something which we call as absorption. The probability of this absorption happening will actually be represented by, let us say, P ABS, and this will be proportional to two parameters. And what are those parameters? One is the density of the incoming photonic radiation, and the second is the total number of atoms that are available in the ground state. And hence we can write down that your P ABS is equal to A12 rho into N1, wherein A12 is nothing but the Einstein's coefficient for absorption. So this is one of the ways in which matter will interact with the atoms. Another way in which it will interact is this one. Once again, the similar situation, and this atom which is now in the excited state, it will once again move back into the ground state and it will release this particular photon, which is equal to of energy h nu. H is the Planck's constant, nu is the frequency of the photon. Such a kind of transition from the higher energy level to the lower energy level without any external trigger, this is called as spontaneous emission. Spontaneous emission. And the probability for this spontaneous emission, we will represent it by the factor something like P SP dot EM. This probability will actually be equal to B12 into N2, because it is dependent only on the total number of atoms which are present in the excited state, and hence it is represented by B12 N2, wherein B12 is nothing but the Einstein's coefficient for the transition from the level 2 to the level 1. To be more precise, let us write this thing down as this is going to be equal to B into 21 into N2. So this is going to be my probability for the spontaneous emission. This is going to be the probability for the absorption. There is one more way in which radiation will interact with matter, and that is the third option that we are considering. In this case, we already have these photons around, and one of these photons will actually trigger the bringing down of the transition of an electron from the higher energy level to the lower energy level, or rather the atom from the excited state to the ground state. In this case, as we have studied further, there will be one photon which will be this, and there will be an additional photon that will be liberated due to the transition of the atom from the excited state to the ground state. So this is actually such a kind of transition, as we know, is called as stimulated, because this is stimulated by the external factor, and in this case by the photons. The probability of the stimulated emission represented by Psm.Em will be equal to C21 into rho into N2, because it is dependent on the density of the photons that is actually falling on it. It is also dependent upon the total number of atoms which are there in the excited energy level. And thus our expression is given by Psm.Em is equal to C21 into rho into N2, whereas usual your C21 is the Einstein's coefficient for stimulated emission, and over here B21 is the Einstein's coefficient for spontaneous emission. We now have three equations over here: the probability for the absorption, the probability for the spontaneous emission, and the probability for the stimulated emission. At equilibrium, the probability for the absorption should equal to the sum of the probability of the stimulated emission, in this case the spontaneous emission. At equilibrium, at thermal equilibrium, the probability of absorption is equal to the probability of the spontaneous emission plus the probability of the stimulated emission. We now simplify this equation further by substituting the respective values over here. We now substitute the values in this equation. The probability of the absorption is given by the equation A12 into rho, which is the density of the photons of a particular frequency, multiplied by N1 is equal to probability of the spontaneous emission, which is going to be equal to B21 into N2, and plus the probability of the stimulated emission, which is going to be equal to C21 multiplied by rho multiplied by N2. We simplify this equation further. So we simplify this equation further to obtain rho is equal to B21 into N2 divided by C21 into N2, and this is once again A12 N1 divided by C21 into N2 minus of 1. These cancel out over here. We now substitute the values for N1. So from the Maxwell-Boltzmann statistics, the total number of energy levels, or the total number of atoms with energy levels N1 in the ground state are given by the factor exponent e raised to minus of E1 upon kT, wherein K is the Boltzmann constant and T is the temperature. Similarly, the total number of atoms, we are speaking the total number means this is going to be a statistical number of atoms in the excited state with energy levels E2 is given by, once again, by the Maxwell-Boltzmann factor E2 upon K into T. So we now substitute these particular values in this equation and simplify it further. We now substitute the values for N1 and for N2. and hence your rho, let us be more specific for rho, let us write rho for a particular frequency is equal to B into T1, the ratio of the Einstein's coefficients, divided by A12 divided by C21, and this is N1 upon N2, and therefore this is going to be equal to exponent of minus E1 and plus E2, and this entire thing divided by KT minus 1, which will now simplify to B21 upon C21 divided by A12 divided by C21 into exponent of E2 minus of E1 divided by KT minus 1, and this is your rho V. The density of the photons of a particular frequency is given by this particular expression. Let us call this expression as 1. From the blackbody radiation or from the Planck's theory, we have the density of the frequency as equal to 8 pi h nu cube upon c cube divided by 1 upon e raised to e2 minus e1 upon kt minus 1, and let us call this particular expression as 2. When I compare these two expressions, because since the left hand side is equal, I can very well compare these particular expressions over here, and immediately I can understand from here that your B2 upon C21 is equal to the factor 8 pi h nu cube upon c cube, and we are comparing actually the coefficients over here, and over here you can understand, if you can check this out, that the coefficient of E over here is 1, over here it is A12 upon C21. Hence, comparison of the two, A12 upon C21 is actually equal to 1. That is, A12 upon C21 is equal to 1, or A12 is equal to C21. Let us now analyze these two results further. So A12 upon C21 is equal to 1. That is, C21 is equal to A12. Now let us find out the ratio over here. That is P of the stimulated emission, that is the probability of the stimulated emission as compared to the probability of the absorption, is equal to, we know that probability of the stimulated emission is given by C to 1 multiplied by rho multiplied by N2, and this is divided by A12 multiplied by rho multiplied by N1, and this simplifies to rho and rho will get deleted, and C21 is equal to A12, and hence this simplifies to N2 upon N1. Once again, this will work out to E raised to minus of E2 upon KT, and the one below will work out to E raised to minus of E1 upon KT, which we can simplify it to be E raised to minus of E2 minus of E1 divided by KT, and this turns out to be, this entire expression will now turn out to be E raised to minus of h nu upon KT, wherein h nu is nothing but a photon that is liberated of energy E2 minus E1, because that's where it is going, it is making a jump. because that's where it is making a transition from the E2 level to the E1 level. When I substitute the values in this expression, the probability of the stimulated emission to the probability of the absorption turns out to be 10 raised to minus 44 if we are taking lambda is equal to approximately 5000 angstroms and your temperature is your room temperature, which is going to be equal to 300 K. This figure suggests that the probability of the stimulated emission to that of absorption is as low as 10 raised to minus 44. That is, it is extremely low, and therefore it is not going to occur naturally. We will have to stimulate, or rather instigate or enforce stimulated emission in order to cause something which is called as population inversion, which is the condition that is required for the lasing action to occur. Sincere thanks, students, for watching this particular video. Stay tuned to Ekeeda and do subscribe to Ekeeda. Thanks a lot.